I'm going to spend the bulk of my time on Python 2.5, which is going to come out somewhere this fall. Then a few tidbits of Python 3000 news, although I recommend it if you want to know more about Python 3000, come to the O'Reilly Open Source Conference this summer, because there I'm going to do a keynote completely on Python 3000, and hopefully I'll have some actual information rather than just plans and ideas. And finally, we'll open it up for questions. I do have to apologize, I have a terrible cold. If someone could bring me a glass of water, that might be helpful at some point. So, Subversion, a year ago we were still using CVS, and we thought we were happy, but it sort of, yeah, just pour it into the laptop. It was beginning to crack at the seams. And SourceForge wasn't providing us with the service we really wanted. I mean, they were in a constant capacity crunch. And some of the things they did were really unpleasant. For example, they introduced a long time delay between check-ins and the results of those check-ins being available in the read-only repository that most people use when they're not active developers. Also, SourceForge had been promising to offer Subversion for a very long time, and they weren't delivering on that. Actually, I got the email yesterday that they finally opened up their Subversion support. But we couldn't wait for that, so we just decided to host it ourselves. After a lot of hemming and hawing and sort of soul-searching, the PSF decided that we could host it ourselves, and it's been very successful. You can go to the python.org/dev website to find out exactly how you can check out Subversion stuff. You can, of course, go to the Subversion website to learn about Subversion, the new branching model. It's been all, I mean, I've been very happy with how the transition was done. Very smooth. All the old history, of course, is completely maintained, complete with all the comments, branching information, checking dates, checking authors, and everything. So now the last thing that still hooks us to SourceForge is the bug or patch manager. And I have a feeling that maybe a year from now we'll be using something else instead of that as well. But there aren't any concrete plans just yet, so I'm just hopeful. So I had a slide layout problem. I wanted to show you some screenshots, but this is pretty much essentially vertical piece of information, so I decided to put the title on the side. What you see on this slide is just a snapshot from the build pod. The build pod is a distributed piece of software where a number of people, mostly volunteers, run a cron job or some kind of continuous process that checks out the latest version from Python version from Subversion, goes through the entire build process, make clean, configuration, build the tests, and reports the outcome from that to a central server that then turns it into HTML with some style sheet stuff. So here you can see, I don't know if the font probably isn't readable, but each column corresponds to one machine. The machines on the left are the machines running the 2.5 build job. On the right, we also have machines running a 2.4 build job where there wasn't any activity recently when I took this snapshot. On the very left, you have a timeline. The second column is mostly what activity done by whom caused another build to be started. You'll see Georg Brandl checked something in around 10:17 in the evening. I don't know what time zone that is. Imagine, oh, it says GMT actually. And then all the build bots, the various build servers immediately started checking that out and building the new version, and all except for one ran all the tests successfully. This is very useful because it means that if someone makes a check-in and they forgot to run the unit tests, or maybe they did run the unit tests and everything was fine on their platform, but they accidentally broke something on one of the other platforms to which they don't have easy access to. This will be found out pretty much in the time that it takes to check it out and build on that machine, because the build bot machines are pretty much responding instantaneously, if I understand it. So every project should have one of these, and this has been very helpful in making sure that sort of the recent 2.5 activity, there was a lot of activity, and the build bot has really helped making sure that if there were any problems with particular check-ins, that they were fixed very quickly, because everybody can see what's going on, and it's completely clear which check-in caused problems if there were any. Without laying blame, we're not saying, oh, you broke the build, you can't check in anymore, you have to fix it personally. It's just a matter of sort of keeping the quality of the code up. So another project that actually has been active for quite a while, but it's sort of slowly growing into maturity, is the cheese shop. Not everybody likes that name because it has the suggestion that there isn't actually any cheese being sold there. If I read this screen, there are currently 1,201 packages in the cheese shop, so there is definitely a lot of cheese, not just hamburger. This works especially well in combination with certain other automated tools like the easy setup stuff from Philip Eby, which lets, for example, the Turbo Gears folks produce a distribution that's a relatively small distribution by itself, but that contains links to various other packages that are all downloaded from the PyPy or Cheese Shop archives. And all the right versions are, I mean, there's a lot of metadata and all this is geared towards making this as easily possible to automate. So you don't have to manually do a lot of stuff to get the right version. And all the dependencies are explicit in the distribution information. So basically, I'm encouraging anybody who isn't exposing their code through the cheese shop yet to go there and put in their packages so that other people can benefit from this wonderful system. And then the last one is the new Python.org site, which is currently still in beta. It's been in beta pretty much since last summer. But it's going to go live a week and a day from now. Next Sunday, it's going to be live. And we need help. We have all the design, all the tools, everything is done. The one thing that is lacking is complete content migration. A lot of the content has been migrated, but the migration was done as sort of as a test case rather than to actually get the live site up. And so there's a lot of content that still has to be migrated or has to be migrated again because it was updated on the original site. So during the sprints next week, one sprint track is going to be worked on the new Python.org site. If you want to help, please send email to py.org and python.org and participate in the sprint however you can. You can certainly sprint from home or from work if you're not staying for the sprints at the conference. So that was my announcement. So Python 2.5. We have agreed on a release schedule. We also have some potential modifications to that, but there is a release schedule, and I'm going to say a whole bunch of stuff about what's new with that version. So the release schedule, the current proposal is we're going to have 3 alphas, 2 betas, 1 release candidate, and if that release candidate is good, a final right after that. So the first alpha would be on in the beginning of May, where we have very exact dates here. I don't know if we'll make those exactly. Then everything is paced approximately 4 weeks apart. That's a pretty tight schedule. One thing that we may actually do, Anthony Baxter, our release manager, he's been doing a great job as release manager, so we're delighted that he's doing it again. He says he actually probably wants to do the alpha 1 sooner. And if we get enough features completed in next week's sprint, that's a serious possibility. And if we start the alpha sooner, then hopefully we can also do the final release a little bit sooner. Maybe the whole thing can even be shifted up 3 or 4 weeks. In related news, Anthony also told me that he wants to do 2 more releases of 2.4. One pretty much very soon, before the 2.5 alpha. You can't do 2 releases at the same time because it's the same people that have to do the work. So we're going to do the 2.4.3 before doing the first 2.5 alpha. And then the last 2.4 bug fix release, 2.4.4, should come around the same time, either before or after 2.5 final. And then after that, unless there's something really dramatic that requires us to put out a security upgrade, 2.4 is end of life. I mean, we've been putting out 2.4 releases for 2 years by now. So that's the release schedule. So what's going to be in that release? And I think 2.5 is one of the biggest releases we've had in a long time. Probably more things than in any of the recent releases since 2.2. So we have, well, yeah, I shouldn't be talking too much over this slide because this is just the table of contents of the rest of the talk. So we have import stuff, a whole bunch of new syntax, modified syntax. Also a bunch of interesting developments in the implementation that don't affect the language, but help development quite a bit. So, absolute and relative input. That's actually, this PEP was slated for inclusion in 2.4. All the design work was done, the PEP was written and approved. The PEP contained 2 parts, and someone implemented the first part, which was a very simple addition to the syntax where you can say from blah blah import something, something else, and then that last phrase you can put inside parentheses so you can break it across multiple lines without using backslashes. That was a very simple syntactic change, and that made it into 2.4. But the meat of the PEP somehow got lost. Nobody volunteered. We had to get the release out. So that one's a year late. 2 years late. I think the PEP hasn't been updated yet. The PEP has a particular timeline that looks overly aggressive if you don't realize that everything has to be up by 1 release. So, in short, the problem is that if you say import foo in a module that is itself part of a package, it looks in a number of different places. First, it looks inside the package. So it looks for a sibling module. If I can't find it there, it looks on sys.path, so it looks for a top-level module. This causes all sorts of ambiguities. Sometimes you have a top-level module with a certain name and the module inside the package with the same name. And at some point, someone will want to, inside that package, will want to import the top-level module by that name because it contains functionality that they need. And there's no way to do it because they say import foo, they'll always find the foo that's inside the package. And this can happen sort of in different situations where a package is evolving. Maybe initially you didn't even know that that particular global package existed. It could also be that you actually didn't realize you were using it, and then you created a local submodule that had an accidental name conflict, and suddenly other code starts breaking. So we needed a way to disambiguate this, and the only really realistic way was to sort of have explicit syntax where you say this. If you write it this way, it's an absolute import, meaning it only looks for top-level modules and packages. If you write it that way, it's a relative import, and it only looks inside the package. So after a bunch of different proposals, we decided that you can say from dot import foo, or from dot dot, or from dot bar, or dot dot bar. If you have deeply nested packages, you can use as many dots as you need to reach up in the package tree. Although at some point you would be introducing as many dots as necessary for an absolute import, and I don't think we're going to make that legal. We almost have a patch ready for this. Thomas Wouters just admitted last night that he had done the patch, but he hadn't actually read the PEP all the way through, so there are a few syntactic differences between the implementation and the PEP, and I'm sure we'll get that straightened out during the sprints. Oh, one thing, because this changes the semantics of a regular from x import y or just import x dot y. In order to trigger the new semantics, you have to say from under future under import absolute import. Now I think that the syntax with the dots will always be allowed, but the syntax without the dots will change its meaning depending on the presence of that future state. I think people have probably been asking for this for at least 15 years. And I've been very reluctant, and I'm still reluctant, because it leads to a style where people try to cram as much as possible on one line of code, and to me that sort of is bad for readability. For example, I remember there's a PEP somewhere that proposes a new feature for 2.5 and it uses conditional expressions, but the code that is the two alternatives and the condition together don't fit on the line, so it has to break this conditional expression across 3 different lines, which to me isn't actually any more readable than just writing if condition, then assign x this value, or else assigning this other value. I mean, I don't know, maybe I'm just more used to if statements than if expressions. Anyway, people just wanted, and there was one particular high-profile bug where in the standard library there was some buggy code because nobody had the author hadn't realized that the true alternative itself could sometimes be false, and then if you use this hack with condition and expression or another expression, it just falls through to the second expression regardless of whether the condition is true or false. Lots of proposals for syntax were rejected, and I chose something that I may still regret this. I really like it at the moment, but we put the condition in the middle and the alternatives are symmetric on the left and the right. Like it or not. Who thinks this is a terrible mistake? Just a quick poll. Okay, doesn't look too bad. Who likes it? A bit more. Everybody else couldn't care less, or they aren't doing it, and I'm glad to hear that. So, use it where you can't constrain yourself. If you have to write a conditional expression, use the conditional expression syntax. Don't use and or. But if you can get yourself to just write an if-else statement, do it that way. So, a pretty minor point. If you have the need for a particular block to be enclosed both in a try except and in a try finally, you would have to actually nest 2 different try statements inside each other. The interesting thing is that years and years and years ago, when I first introduced the try except and try finally syntax, I allowed them to be changed, just like what we're reintroducing now. But at some point, I think maybe some users were confused, maybe I was confused myself, or maybe I found it really difficult to generate the correct bytecode, because if you combine them, the implementation has to sort of set them 2 different exception handling contexts, one for the except, one for the finally. You can't have the same exception handling context handle both. And because of that, in the implementation, I decided that it was easier to force people to be explicit. And years later, I spent a couple of years writing a lot of Java code and realized that Java allows except and finally to be combined in the same try statement, except they call it catch. And I looked up their documentation and I realized that there's absolutely no ambiguity if you put the finally at the very end. Syntactically, the finally has to be last if it's there. And if you do it that way, it's completely clear that the finally happens even if there's an exception in one of the exception handlers of the except block. So this was actually a pretty brief discussion on Python dev. We finally got someone to also implement this, and it's now in the Subversion head. Much more exciting and
bigger in scope and more dramatic is a bunch of enhancements to generators. Philip Eby did a lot, not just implementing this, but also rewriting this part of the PEP and sort of helping me understand the requirements and the implementation choices. So in 2.4 and before, yield is a statement. It requires an expression. And it has the particular requirement that the initially hard to understand requirement that you cannot have a yield inside a try finally block. This all has to do with the fact that we could not guarantee that the finally clause was executed in the following situation. You have something that yields a bunch of times, and that generator is used in a for loop. Now, someone breaks out of the for loop before the last element of the sequence has been generated. Then the generator is suspended at that yield, and then for loop exits, and that just garbage collects the generator object. And we didn't have any way to sort of pass control back into the generator to clean up. So that basically we would just throw away the step frame without ever executing the finally clause. So we figured it wasn't fair to allow people syntactically to write a yield inside the try finally, but then not actually execute their cleanup code. They might be sort of bamboozled into believing that they could use that to acquire a lock, yield something, and then in the finally clause release the lock. I don't know why you would do that, but you could write that code and you would expect that you had a guarantee that the lock would also always be released. Well, it wouldn't be if someone just got one value out of your generator and then threw it away. So after lots of discussion, we realized that there were actually ways to sort of work around this. I guess it took a couple of years of experience using generators to really appreciate that the need for finally clauses is real, and also the need for handling exceptions sometimes. So now we have a number of new features. Yield is an expression. Of course, you can still use it as a statement, just like any expression can be used as a statement, but you can use it as an expression. Usually you have to put parentheses around it, but you don't have to pass it an expression. So what does yield return when used as an expression? Well, if you use it in a for loop, it'll just return none, so that's not very interesting. However, the generator now has a new method named send, which takes one argument, and that send argument is passed into the generator, and that's what it returns when you yield it. If you can't follow this at this point, don't worry. Go back to the PEP and read it. It explains it much more patiently and clearly than I can possibly do with a few slides. But the net result is that you can now have actual code routines that pass values back and forth. The generator yields a value to the partner, and the partner then uses send to pass a response back into the generator. You can go back and forth that way. Instead of sending a value, you can now also send an exception. We didn't want to do a type check, so we actually have a separate method. We called it throw because we couldn't call it raise.
Raise underscore.
Yuck. He said raise underscore. So you send an expression into the generator, and it does exactly what you sort of would expect that to do. It resumes at the point where it was suspended, which is always by definition at the yield, and then it will look like that yield actually raised that exception. So you can have exception handling. You can also have a try finding clause for cleanup. The interesting thing is, if there is no exception handling in the generator, then throw will raise that exception right back out of out of the throw method. So g.throw of some exception is pretty close to actually raising it, except it also passes through any try finally clauses or exception handling in the generator. So actually, a pretty common pattern that we recommend using with this is for the generator to use it for cleanup, but then re-raise the exception. This example doesn't do that. So there's a little more detail. Let's see, I mentioned yield as expression, send, throw. Oh, so there's another new method, which is just a sort of little bit of syntactic sugar around throw. You can call close on a generator, which raises a specific exception named generator exit. And then in addition, if the generator responds by raising that exception right back at you, close will catch that and ignore it. So close will not raise the generator exit exception. It will just sort of assume that the generator did its cleanup and then continue. So now that we have the close method, we can also define what happens when the generator is just garbage collected. When it's garbage collected, like you use it in a for loop and at some point you break out of the for loop before the generator is exhausted, then behind your back, when the last reference to the generator object is removed, we actually call its close method. Now if at that point, somehow, it's possible that close generator exit and then the generator hits some code that wasn't supposed to be executed and it tries to divide by 0 or it throws a key error or something like that. We do the same thing whenever there's an exception raised in a destructor. We just print a message with a little traceback and then we swallow the exception and continue because there's no, sort of the interpreter doesn't allow us really to percolate that kind of exception back up. So there's nothing really new there. We just had to sort of get over the fact that that's going to happen in this case too. And so now everything together means that you can happily put a yield inside the try finally, and you will be guaranteed that that finally clause will be executed. Not necessarily exactly at the time you wanted it, because if the generator is involved in a memory cycle, then it will only be closed when the real garbage collector actually starts cleaning up the cycles. But the finally clause will eventually be called. And sort of the crown of this work, and this originally was in the same PEP proposing the generator enhancements, and it was proposing more, and it became a little too ambitious, and then Philip Eby's contribution was to sort of pare it down a little bit and break it up into two separate PEPs. This is the with statement, which, well, here I'm just showing what the syntax looks like. You say with expression, and then optionally you can say as some variable, and then you have an indented block. And there's code, the second half of the slide shows you what that expands to. The motivation for this is, and this is something that happens a lot with mutexes or locks or condition variables, but there are plenty of other places. It is very powerful syntactic sugar for a try finally, where there is some action before you start a block, before you enter a block, which requires corresponding cleanup to happen after you leave that block, whether you leave it normally or through some exception. And of course you can write, I've written it 1,000 times. mutex.acquire, try, code my critical section, finally, mutex.release. However, this is somewhat painful. It is a bunch of extra lines of text. I mean, it's much easier to just write mutex.acquire, critical section, mutex.release. You don't have to indent your critical section. You don't have to type the words try and finally, and you save 2 extra lines of code. And it's sort of attractive to write that code, even though you know that it's buggy, because you think, well, this is a bit of throwaway code, and I'm not actually being invoked by anything that's going to ever catch exceptions, or maybe I know that I think I know that my critical section is never going to raise any exceptions, so I can sort of save myself the bother of typing the try finally. This is almost always a mistake. I have done this myself many times and always regretted it, and had to go back and sort of look up at every single place where a mutex was acquired and figure out where the corresponding release was and indent all the code and put the try finding syntax in, because sooner or later you always end up being stuck with a mutex that was acquired but not released because you were too lazy. So the motivation for the with statement is to sort of make the laziness no longer an argument for not doing the right thing. We introduce syntax that sort of, it doesn't explicitly do the acquire and release actions. You just say this object as a context manager and this block executed under the guidance of that context manager. And the syntactic sugar makes sure, the expansion makes sure that the acquisition and the release always happens. And of course you can use this for all sorts of things, not just for acquiring locks. There are other examples where you commit or roll back database transactions, or where you even just opening and closing a file is a useful thing. Decimal contexts are another example. The design went through a number of iterations. Initially, we didn't realize that the context manager would have to be a separate object from, or at least potentially a separate object from the sort of the thing whose context is being managed. And I think it was some use case from the decimal module that made it clear that the context manager had to be a separate object. So the expression that you put in the with statement evaluates to some object that is itself not the context manager. You call its under context under method, which gives you context manager. Now, if the object and the context manager can be one and the same, it's very easy. Under context just returns self. But if you have a need for something else, you can create another object and do it and use that. This is sort of the same as the difference between an iterable and an iterator. So you can have multiple iterations over the same iteral going on in parallel or nested. So the context manager has an enter method, which is called with no parameters. And it can return a value, and if it does return a value, that value is assigned to the variable that you optionally specify in the with syntax. If it doesn't return a value and you do have a variable, that variable just becomes none. There's also an exit method which actually takes 3 parameters which correspond to the information that we typically pass around for exceptions. So the exit can take a different action based on whether the block was left through an exception or completed successfully. And the only use case we have for that is potentially, if someone has a database module, they may have to have some kind of automatic commit of transactions when your code succeeds, with an automatic rollback of transactions when the code fails. That use case is not actually implemented anywhere, but we see it as a real possible use case, so we decided to let the API have access to all the exception handling information. Normally, all the things that are actually being added to the language will not use that information. There's also there's going to be a decorator that lets you use, and this is where PEP 342 and PEP 343 get together. You can use a generator through into the mediation of this special decorator to become the context manager. So the idea is that a typical context manager sort of does the following. It has the following pattern. There's some setup, like opening a transaction or opening a file or acquiring a mutex. Then you pass control to the block in the with statement. And then you come back and you take over control and you do your cleanup. It's perfectly possible to write that as a little object that has some state, and the under enter is called and it changes the state to I'm initialized, and then under other exit checks that you've been initialized. But oftentimes you sort of, it's very readable if you just write this in the form of setup, try finally, cleanup, and then in the body of the try finally, you put a yield, and the yield is replaced by, is sort of logically, conceptually replaced by the body of the with statement. And if you yield a value, that value is assigned to the variable that appears in the with statement's header. So now you can write something like with opening file name as f, and then you have a local variable f that represents an open file that you can use, and when you exit that block, the file will automatically be closed. So the PEP proposes a specific set of standard objects that will become or get context managers. All the mutexes and lock styles in thread and threading modules will be able to be used like this. You just say with lock critical section. There's no point in using the as phrase here, because there's no additional state that comes out of acquiring a lock that you would want to name. So here you just use with lock. Then the decimal module will have a context manager that will let you modify any decimal context information for the current thread for the scope of the with statement. And then files, even though on the previous slide I gave an example where I had a separate method named opening, that was just for sort of as an example of how you would use this thing, this generator pattern to create a context manager. Actually, we're going to give the file object itself an under context method that will just return the file itself. The file is managing its own context. And when you exit, basically the enter does nothing, and the exit will close the file. Now, there was a particular sort of wrong pattern that people were worried would be written by people who don't understand exactly what's going on. But since that, as soon as you write that code, your program is going to crash on the second with statement because the file is already closed. There's really not a whole lot of worry. It's not the kind of bug that will silently be lurking in your program for years until it finally gets triggered. So another one, this actually, I don't remember if I introduced this last year at PyCon or at a later conference. But somewhere last year, we had, right before one of the conferences, we had this wild discussion on Python dev about reorganizing the exception hierarchy and fixing all the problems with the try except statements and exceptions being caught at the wrong time. And right after this, so I sort of gave a summary of the new hierarchy at my keynote in the conference, and right after the conference, we sort of realized that it was too ambitious, not actually necessarily solving the problems that we were trying to solve, and introducing a whole bunch of incompatibilities for no good reason, except that maybe some people thought that the exception hierarchy should be different. So we scaled back the proposal, and this one has the general agreement of Python dev. And I should thank Brett a lot for pushing this one through after the disappointing result with the previous versions. So there are really sort of a couple of parts to it. One is exceptions should be new style classes. Exceptions are the last bastion of classic class use in the standard library, actually in the language, which is annoying and painful, and sometimes causes people to sort of have to write somewhat unpleasant code. I mean, if you have a whole framework that is based on new style classes and certain functionality that only works with new style classes like properties, then it's painful that suddenly you have to remember that you can't use that with your exception objects because they're classic classes. So they'll become new stock classes. That's the first part. That's completely, that was never controversial. We will eventually, and this is going to be several releases before we reach that point, require that all exceptions, user exceptions as well as system exceptions, inherit from a common base class. This is very unusual in Python, where we're big on duck typing. We say as long as you satisfy an interface, if you implement a particular protocol, if you have an append method, you can be used wherever something that needs an append method is required, is using it. For exceptions, however, it turns out there's a very good reason to have a hierarchy with a single root, because the hierarchy is not just used for functionality of exceptions, it's also used for catching, for grouping, and it's important to be able to have a single statement that catches every possible exception. Currently, the only way to catch all possible exceptions is to write except colon, but then you don't have access to the exception object, which is painful. So we have this sort of clumsy function in the sys module that provides you with access to the exception object. But that's a rather roundabout way, and it would be much easier if you could just say except base exception, comma, E, colon, and then you know that E is your exception object, and in every possible exception is caught that way. So in Python 3000 and possibly in 2.8 or 2.9 we'll reach that point. Until then we'll be working on sort of deprecating and finally removing string exceptions and first warning about and then enforcing the requirement that exceptions must inherit from base exception. So the final thing, sort of the middle bullet that I didn't touch on yet, is a slight rearrangement of the exception hierarchy, where the actual root of the exception hierarchy is called base exception. The exception that we expect and recommend everyone to use for the base class of user-defined exceptions, and which is the base class of most standard exceptions, system exceptions, is named exception, which is the current root of the system hierarchy and what de facto most code that declares exceptions derives from exceptions. So you're in good shape if you're already following best practices with regards to exceptions. However, having a separate base exception that's one level up in the hierarchy makes it possible to move keyboard interrupt and system exit around, so they actually inherit from base exception instead of from exception. The reason for that is that it's very common to find code that pretty much catches every exception except those two or except one of those two. There are a number of reasons where catching keyboard interrupt as part of catching everything else is usually not what you intended to happen in your application, because you want the keyboard interrupt just to print a stack trace and exit the application, and you want system exit to not print a stack trace and exit the application. So they're pretty similar in that respect as well. So once we have all exceptions inherit from base exception or exception, and most exceptions actually inherit from exception, the pattern will be that sort of the best practice is if you have to catch all exceptions rather than a specific exception, you'll write except exception colon. And that will catch everything except those few exceptions that need to pass through everything or almost everything, like keyboard interrupt and system exit. Of course, there's the possibility that users will somehow misunderstand this and write regular user exceptions that inherit from base exception. Well, we can't really sort of do anything about that except document that that's not what they should do unless they know what they're doing. So maybe, and this is not cast in stone, maybe we'll actually just remove the bare except from the language. We can't remove that until we actually have enforced the single exception root, because until then, if someone is not playing by the rules and they're still throwing a string exception, or they're throwing an exception that doesn't inherit from any of the base exceptions, there must be a way to catch those. There are legitimate reasons to catch every single exception that could could possibly dethrone. So as long as we don't have the enforced single hierarchy, we still have the bare except statement. But eventually we'll get rid of that. I think the string exceptions are the first ones to go because they've been obsolete for such a long time. But it will still take 2 releases to deprecate them. And the interesting thing is deprecating the raising of an exception can be done in 1 release, but you can't deprecate the catching of sort of a bad exception type until the next release. Because I may be writing all my code clean and not using any deprecated features, but I may still have to catch an exception that someone else declared in code that I don't have control over. So their code gets the deprecation warning, but my code shouldn't be penalized with the deprecation warning. Anyway, it'll take a long time, and you can read the schedule in the PEP. And maybe we'll just cut that short and go to Python 3000. So one of the last ones is under index. So here at least, there's a very clear use case. In numeric Python, they define their own scalar index integer types, in part because they want to represent the fact that if it goes into an array, it's an array of integers of a certain size, and they really care about space efficiency. So if they only need 16 bits, they don't want to store 32 bits like a million times. Also, they have this use case where a scalar is really a rank 0 array, and certain standard operations that apply to all numeric Python arrays, like asking what is your rank, also must apply to their own integer types. So anyway, they discovered that they couldn't use their integers as slice indices. They could make it work so that if you use them as a sequence index, a single index, that works fine. And of course they can make it work. They can overload addition and all the arithmetic operations, so you can do mixed arithmetic with Python's built-in integers and their own integers, and the right thing will happen. But they found they couldn't use them as in slices, because when you have a sort of a classic slice with a single column, the virtual machine requires that each of the slice expressions is an actual integer or long integer object. And so of course they came to me and they said, could you please change that code to call under int when it's not an integer object? And I said, no way, because then if you use 3.5 and 3.7 as slice indices, you'll suddenly get a silent empty slice rather than an error. You can't use a floating point number as a slice index dummy. So they came back and we negotiated a bit, and I said, well, but I could introduce another API that your integer type and maybe some other integer-like types could implement. And we decided to call it under index under because pretty much the prominent use case is as slice indices, although there may be some other places. And this looks like it's a fairly small amount of work. Most of the changes are in 1 or 2 places only. The PEP is close to completion and acceptance. The implementation patch is being worked on in parallel with the PEP, so that's a nice little problem solved for the future. I mean, some people have said, why don't you just change under int? The problem with that is that it would break so much code that expects the current behavior when you call under int on a float or something else. It really shouldn't be convertible to an int without it. I mean, the problem with under int is that sometimes it's a type conversion and sometimes it's also a value conversion. And it's a problem we inherited from C, but we can't sort of fix that problem in a compatible way. So that's why we have to use a new API in this case. So the remaining 3 things are not really changes to the language. Well, they are changes to the language at all, but they're interesting developments in the implementation, the CPython implementation at least. So for many years we've had the infamous AST branch, which was an alternate bytecode compiler, and it was bigger and better and much easier to use, but it wasn't quite working yet. And we were very close to implementing that, to merging that branch back into the head for Python 2.4. but the people responsible weren't confident that their code wouldn't break anything, and it was getting very close to the 2.4 release, and there was no way to really spend a lot of time to guarantee that it wouldn't break anything, so we decided to put it on one more release. And I think last fall at some point, somebody said, so what's the status of the AST branch? And nothing had really happened on it for a very long time, and I sort of said, okay, let's just declare the AST branch dead. It was a nice idea, but there doesn't seem to be enough energy to ever make it move forward, so let's just officially declare it dead. And I think within a week of that, it was integrated into the main branch. So actually, the same thing is happening with the new Python.org, by the way. That was also very close to being dead for lack of energy. But now it will happen. So this new bytecode compiler uses a much more efficient and useful data structure to represent the source code. I mean, the old compiler represented the source code as a tree, but there was a tree that contained every silly detail, every token, every character that was in the input, as long as it wasn't white space or a comment, was represented in the parse tree. So it's very cumbersome to traverse that parse tree. It also represented every level of operator priority, whether or not operators of that priority were actually present. So an expression with three operators would contain, I don't know, probably 30 levels of tree nodes that were mostly empty. The new syntax tree makes that much easier, so it's also, in theory, it should be faster. Do you know if the new bytecode compiler is faster, Jeremy?
I believe it is.
Okay, well, that's good enough. That's the kind of accident that I like to hear about. So, one of the main arguments for having this new compiler is that the old bytecode compiler was really hard to maintain. Nobody really was familiar enough with the data structure and the strategy used for compiling bytecode that there were only very few people who could implement new syntax in the language. And it was getting a bottleneck. And we've already had sort of random volunteers come up, say, can I help implement some language change? And we said, sure, here's the new AST bytecode compiler, here's a piece of syntax, try to putting that in, and it came out really well. So that was actually, I think that was a success story. Another success story is 15 years ago, I wasn't really aware of 64-bit machines as a sort of a realistic alternative. And I certainly wasn't expecting that people would anytime soon build machines with so much memory that 32 bits would not be sufficient to index a string. Well, it's happened. Google has lots of machines that have lots more memory than 4 gigabytes. And other people do too. So there were actually, the problems about using an int to represent an index and to represent the length of a string and a sequence in general weren't entirely theoretical anymore. So Martin van Loos proposed to switch to using the signed size T standard C type def, and it's only a semi-standard C type def. I don't know if it's part of the new C standard or that it was sort of never completely official, but in practice, not all C compilers, although most C compilers support it. So there's a little bit of if-dev hackery in some Python header file that says if it doesn't exist, well, we'll just use a 1 or something. The idea is that a size T is a very old C type def, and it is an unsigned int that is as long as a pointer, so it can index every byte in memory, assuming that the pointer can index every byte in memory. The S size T is a signed version of that. Because Python indices can be positive as well as negative, because if you use a negative index, you count from the end of the sequence, so there's no way around that. So on a 32-bit machine, this is not actually going to help us index more than 2 gigabytes of string data. Now on a 32-bit machine, I'm not too worried that one will write a Python program that reads in 2 gigabytes into the heap and still has room for other stuff. But on 64-bit machines, I mean, if the machine has a main memory of 10 gigabytes, you could certainly imagine filling 3 gigabytes or 7 gigabytes with a single string. And currently, you just couldn't do that at all, because the int was still 32 bits. Ironically, you couldn't use a long either, because on Windows 64, the long is also 32 bits, because Windows sort of has a special meaning for long in all its system APIs that they couldn't change in their 64-bit architecture. So we really had to use a different type. Anyway, it's possible. If you want to, you could even use this to index a list with more than 2 gigabytes, with more than 2 billion elements, although even if it was 2 million elements that were all the same, you'd still need like 16 gigabytes of memory for a list of 2 billion elements. So that's still unlikely, but we're ready for the future. We're ready for Moore's law. At least for one generation. So the final one, this is a little bit of standard library work and a little bit of command line tweakage. In 2.4 we introduced the -m option, which is actually pretty useful for a number of standard library modules that have a little main program like profiling and PDB, the debugger. But people complained that if they had their special main inside the package, and even the standard library has 1 or 2 of those in the test package, and lots of people who distribute third-party software have various sort of useful applications just stuck inside the package as modules. And the -m option wouldn't work with those because it's too complicated to. Well, it was using a particular implementation strategy that didn't generalize to modules inside packages. So Nick Coughlin decided that he didn't like that situation, and he tried to look for a strategy to solve this. And he found a solution in sort of an unexpected place. When I first saw his solution, I was very surprised. But his solution uses a new kind of import hooks introduced by Web 3.02. And not very many people know about these, but if you've ever run into zip import, zip import actually uses this API. And it's an API that lets you find a module inside a package without actually necessarily compiling it to bytecode or executing it. So you're not importing it, you're just sort of getting the code. And so by using these APIs, it's quite easy to write some code that, given a package.subpackage.module name as a string, will find the right module, and then you can say, okay, now I have the code, now execute that code in the context of my under main, and everything is happy. Okay, that's it. Thanks for the timing. So we're pretty close to the end. So one use case is actually you can run the regression test this way once it's implemented. So when I first prepared my slides, I had a whole bunch of information about what's new in the standard library. And then I looked over my slides and I realized that the talk was getting kind of long, and also there's a whole bunch of new standard library things that I don't actually know all that much about. So I'll just recommend that people read about this in What's New in Python 2.5 once it's been updated. I'll just go over the list very briefly. Quantifiers any and all, so you can write if any x in some sequence has a particular condition, or actually you say if any x greater than 5 for x in my list of prime numbers. There's a new profiler, element tree, Frederick Lund's XML API. It will come into the standard library. C-types, which is this scary thing that lets you call arbitrary C code with arbitrary parameters, and so it will also let you cause arbitrary core dumps. But it's been on people's list of requested modules for a long time. Whiskey Ref, I don't know if that's how you pronounce it. WSGI is I think the web server gateway interface, which is, it's a PEP 333, which is a proposed standard for web frameworks to sort of interact with web servers in a way that makes it very easy to switch the web server technology independent from the web framework technology that you're using. This is all Philip Evy's work, and he has kindly agreed to let us use his reference implementation as a standard library module. There are some people who have some suggestions for making it even better, so we may be tweaking that code a little bit. Another Philip Evy thing, setup tools, really easy package management. You may have heard of eggs. The Turkey Gears folks use that. I hear that even Zope is considering to adopt this, which would be a great thing. So I hope that at least basic support for that will be part of the standard library, so people won't have any excuse for not using this new technology for package management. And a couple of distutils extensions. Well, finally, the last week or so, we went through a number of rounds of revisions, and well, this may still be killed during the sprint, but I'm actually pretty hopeful that we have reached the final design here. So the motivating example for this is a data structure that's a dictionary of containing mapping keys to lists of values. And you're basically interested for any key that has maps to a non-zero list of values. You can do it with sets if you want to, but let's just do list for now. Adding a new value to the dictionary is sort of this two-step process where first you say, well, if that key doesn't occur in the dictionary yet, I'm going to have to create an empty list. Otherwise, I have to add to an existing list. So you can write it in 3 different ways, but it's sort of, you have to think a little bit about it. And people have tried to do that using set default. And most people actually, when they see the set default version of that code, they have a much harder time understanding what's actually going on. In part because not very many people are familiar with set default, in part because maybe set default was the wrong name for that functionality. There's also the problem with set default that you can't use set default in the left-hand side of an augmented assignment like plus equals. And also set default takes a default value as a second argument, which is completely ignored when the key is already present in the dictionary. So you sort of create and free an object that you never use. So we've sort of been exploring the design space to somehow make default value pop up in the dictionary at exactly the right moment. So the proposed alternative is that there's a new type called default dict, and it's not a built-in type, but you import it from the collections module. And then you can just say, you can just reference a key, and when the key doesn't exist, some factory function is invoked to produce a new element. And that new element is also inserted in the dictionary. So in particular, the code for adding another value to your multi-map now doesn't have to sort of check for whether the key is there already or not, because that's taking care of the default dict thing. So there were a number of different proposed APIs. Like we could have introduced another version of set default that takes a factory function instead of an actual default value. In the Google source code repository, I found a version of it that took a default value as the argument to the constructor and then actually carefully created a copy of that default value to be inserted into the dictionary when needed. The reason for making a copy is that the most common use case, the default value is a list, but you want to have a new list inserted in the dictionary for each key, so that otherwise it would be a very strange data structure if all keys point to the same list object. So instead of having code that invokes the copy module to carefully make a shallow copy, we decided it would be much easier to just pass in a factory function to the constructor. So that's what we're doing here. And after a number of design cycles again, there's actually some support for this whole mechanism in the dict base class, but in such a way that you can only exploit it by subclassing dict. The point is that the under get item implementation, getting an item from a dictionary, is actually a very subtle piece of code that also has evolved over time. So, and it's very subtle because it's very performance critical, because getting an element out of the dictionary is a very common operation, and you want that to be screaming fast. So we didn't want this addition to slow down dictionary. We didn't want it to slow down the base dictionary type. We also didn't want to duplicate all the get item code into the default dict, because then we suddenly had two places that contained this extremely subtle piece of code for finding a key in the dictionary. Doing it with subclasses, with overriding the method in the subclass also caused problems. That's sort of what you would normally do, but there are sort of corner cases where you get an exception out of under get item that could be confused for the situation where the key doesn't exist, but actually the exception is caused by, for example, a problem in your hash function or your comparison function. So we ended up putting a little hook in the dictionary get item that says, if this class implements a method named under missing, call that method to provide either a default value or raise an exception. And then we optimize that because we know that the dict type itself doesn't implement under missing. So we do a quick type check if the type of the current object is the dictionary class itself rather than any subtype of it. We don't even look for whether that missing thing actually exists because we know it doesn't exist. But of course, default dict overrides it, and so it calls the factory, and it both inserts the value that the factory returns into the dictionary and then returns it. Okay, I have to stop now, so I'll just leave you with this slide. I'll just quickly paste in Python 3000 news. So yeah, I forgot to mention, Lambda is perfect. It will not be removed. But we will also not try to create a better Lambda. We'll use the Lambda that we've got because it's just fine. There's a lot of discussion that has not reached a complete conclusion yet about reform of the string and bytes data types. Clearly, the 2.x situation is awful, where you have two string types, one of which can sometimes be used to contain characters in encoding that you don't know what it is, and sometimes it contains only ASCII data. And we want to improve on that. We're probably going to borrow from Java for that. We're also going to borrow from Java for the standard I/O stack. Not that we're going to repeat Java's mistakes, but we're going to learn from it. And so there will be more 2.x releases. 2.9 is going to be the last one. Okay, it's time. Oh,
one last question for you. How do you like working at Google?
Ask me during the break. I love it.
Good answer.